Welcome to Salts of the Earth, an 8-part video series studying salt attack in adobe and earthen structures. My name is Eric Liefeld, and I'm with Mesilla Valley Preservation. Previous videos in our Salts of the Earth series have covered salt attack, how it works, and how to recognize it. We've also talked about MVP's field test kit that lets you accurately measure salt loads and salt gradients in the field. In this video, we'll talk about remediating salt attack with permeable sacrificial renders and plasters. We'll also discuss several case studies that show how MVP's field test kit can be used to inform remediation and provide greater insights into salt issues in the field. So now that we understand the salt attack process and how to accurately measure salts, how can we use this information to begin to remediate salt issues in adobe and earthen structures? Just as moisture can't explain the damage we see with salt attack, treating moisture alone is often not sufficient. It is important to remember that salt attack is a time-based problem. Destructive salt concentrations typically accumulate over years and decades. If we can effectively remove the salts, then we can significantly set the clock back for the structure. In addition to performing any necessary structural repairs, this means locating and targeting accumulated salts for removal, and/or migrating salts out of load-bearing structure if possible. Of course, we also want to directly address the moisture issues that brought the salts there in the first place. This can mean improving grading and drainage, and identifying and eliminating any water sources. Permeable plasters and renders are an absolutely essential tool to aid this process. So why do we think of permeable plasters like mud and lime as tools? It is specifically because these plasters have the ability to act sacrificially. Not only can they help protect the load-bearing structure of the wall, they can act as an early warning system that lets us notice salt activity before it does critical structural damage. People often worry about moisture, and yes, moisture is a part of the vicious cycle that can lead to salt attack. But as we've seen, moisture alone is not capable of doing the damage that we see with salt attack. Instead, the destructive phase of salt attack is driven by evaporation. Specifically, the damage takes place at or near the evaporative or drying front, where salts crystallize as moisture evaporates. Permeable plasters and renders, such as mud or lime plaster, are useful because they allow the drying front to occur at or near the surface of the plaster. This in turn effectively moves the entire salinity gradient out of the wall and toward the plaster surface. As the gradient moves outward into the permeable render, the highest salt concentrations go with it, and salt concentrations in load-bearing structure are lowered as a result. These diagrams show the critical difference between permeable and non-permeable renders and plasters. As we've seen, salinity gradients are often exponential in nature, with much higher damaging salt concentrations toward the drying or evaporative front. The location of that drying front is critical, and it can be manipulated by choosing the right plaster approach. On the wall cross-section depicted on the left, we see a permeable render, such as lime or mud plaster. The evaporative front is basically at or near the exterior surface of the plaster, as shown by the salinity gradient. This is actually an ideal situation, because the highest concentration of salts are effectively drawn out of the load-bearing structure of the wall. If damage does occur, it will take place in the outer plaster layer. So not only is the plaster layer protecting from exterior erosion from wind and rain, but it also is protecting from erosive salts that come from the interior of the wall. Also, any efflorescence or damage will be visible cosmetically on the surface of the wall, providing an early warning system to alert to any ongoing maintenance needs. The illustration on the right shows the same salinity gradient behind a less permeable Portland cement or elastomeric stucco coating. In this scenario, the damage typically takes place behind the plaster layer, in the actual load-bearing structure of the wall. In fact, the cement or elastomeric stucco layer can appear quite normal, while considerable invisible structural wall damage is done by circulating salts. These two photos illustrate the damage that non-permeable plasters and coatings can cause. The photo on the left shows historical attempts to repair salt damage with a concrete collar and cement plaster. We're looking at a cross-section here where the concrete and stucco have been cut off to allow wall repair. We can see that there have been multiple efforts to repair the damage with concrete. Unfortunately, because the concrete is less porous than the adobe, the evaporation has taken place in the more permeable adobe. The moisture simply takes the path of least resistance and evaporates where it has access to air, behind the concrete and behind the cement stucco in this case. The result is that the damage has continued to occur behind the concrete, inside the load-bearing structure of the wall. The photo on the right shows an example where positive remediation was done initially, and then, unfortunately, reversed. This salt-laden wall was appropriately treated with lime plaster several years ago. The lime plaster has been doing its job and migrating remaining salts to the surface. Unfortunately, the contractor responded to the reappearance of the salts by coating the building in an elastomeric coating. Of course, the salt damage continued behind the elastomeric coating, causing the rubberized surface to bulge and blister. Here is a spot where someone has kicked the elastomeric blister out of curiosity, allowing a stream of salt-damaged lime plaster to flow out. So far, the lime plaster is sacrificially taking the brunt of the damage, but eventually the salts will begin damaging the adobe wall within. Here is a historic adobe building that was ultimately replastered with Portland cement plaster or stucco. It has also had a concrete collar poured up against the base of the wall to try to deal with the salt damage. In the Mesilla Valley, we often call this problem structural plaster, because the plaster is sometimes the only thing that seems to hold up the wall. As you can see, despite layers of cement plaster and a later concrete collar, the adobe wall has simply ceased to exist. All that is left behind is the powdered adobe and the endlessly circulating salts. It will come as no surprise, but this building has now ceased to exist entirely. Sometimes, if you aren't careful about how you remove plaster that has become structural, walls can collapse. Here again is the collapsed wall of the San Jose Catholic Church in El Paso, Texas. Built in 1892, this building had been deemed structurally sound by professional engineers only a few months earlier, and was in the process of being rehabilitated when this collapse occurred. The collapse bears all of the obvious hallmarks of salt attack. Newspaper reports described how contractors removed the cement stucco to find that the wall beneath it had turned to dust. This describes salt attack perfectly. By looking at the alignment of the handicapped parking signs and the plaster mark from the intact portico, it's easy to see how at least a foot of wall height simply turned to powder and disappeared in the collapse. A large concrete collar and substantial concrete patching are in place, indicating past efforts to cope with salt attack. Fresh cement plaster patching shows what the workmen were trying to do. Unfortunately, placing concrete against the base of the wall only served to drive the moisture and salts higher and into the wall structure. The real tragedy is that even with this damage, this structure could have been saved with proper techniques. Unfortunately, the 124-year-old building was subsequently condemned and demolished in 2016. To see how MVP's toolkit can be used to help understand building dynamics, we'll look at several case studies. The first of these is the diocese building for the Basilica of San Albino in Mesilla, New Mexico. This adobe building had been severely affected by salts and had undergone substantial wall damage. A local contractor had repaired the adobe damage several years ago and had placed a band of tinted lime plaster at the base of the wall, as shown in this photo. The lime plaster was separated from the existing cement stucco by a wooden drip edge, which was painted white. Based on the heavy salt contamination, we and the contractor fully expected the salts to reappear after the repair. Sure enough, after several years, some rather dramatic staining had occurred, and the contractor wanted to know the source of the various stains. The contractor suspected that the upper stains were unrelated to salts, but wanted confirmation. We drilled core samples from several of the stained sections. Testing with MBP's toolkit showed definitively that the lower stains were indeed salts, and both lower samples showed the characteristic exponential salinity gradient with a relatively high baseline. However, the third sample showed almost no salt at all, and a much lower baseline. Not surprisingly, that sample was taken up higher on the wall. In fact, the higher staining was coming not from salts at all, but from oxidized white paint falling off the installed drip edge. In other words, the most dramatic staining was entirely cosmetic and not related to salts. Looking closely at the wall of the diocese building, the answers were actually pretty obvious. At the time we took our measurements, the salt-stained areas looked like this. The salts literally looked like frosting and sparkled in the sun. In other words, the lime plaster was doing exactly what it was supposed to do. It was promoting the remaining salt loads to the surface as efflorescence, drawing them out and away from the load-bearing structure. With salts efflorescing on the surface like this, there is an excellent opportunity to collect them and remove them from the site. Maintenance now becomes a simple function of a wire brush and a vacuum cleaner. Unfortunately, many people fail to notice this and take advantage of this opportunity. If no maintenance is performed, These salts will simply continue to accumulate, redissolve in the next wet cycle, and reabsorb into the wall. Our second case study comes from the Nestor Armijo house in Las Cruces, New Mexico. This photo shows one of the worst areas of salt attack. That brown pile you see in the back under the stairwell is literally powdered adobe, and it is about 12 to 18 inches high at its deepest. Interestingly, this dramatic salt damage was occurring at the inside surface of the wall. This is the opposite of what we normally expect. The outside of this wall is under a north porch, which sheds considerable water. At the time, there was a concrete sidewalk, cement plaster, and elastomeric coatings on the outside of the wall. Interestingly, it was clear that coving from salt attack had historically taken place on the exterior of the wall. A small concrete collar had been placed at the exterior wall base. Since that time, a lower lime plaster layer had been covered over with several layers of cement plaster and ultimately an elastomeric coating of some sort. A large concrete sidewalk or apron had been poured up against the building. In addition to the powdered adobe, there was ample evidence of severe moisture and salt issues. These badly rusted pipes were actually once steel electrical conduit that was placed in the walls just a little over 30 years ago. They crumbled to the touch and looked to us as if they had been on the bottom of the ocean. In a way they had, since they had been continually subjected to high levels of salt-laden moisture. Once the accumulated powdered adobe was removed, we sampled the wall at this location under the stairwell. In 2013, core samples were taken from both the interior and exterior of the 3-foot-thick adobe wall, at approximately the same location and height, using MVP's sampling kit. The goal was to get a representational cross-section of the wall to determine where the salts were concentrated. The results showed a very strong exponential salinity gradient toward the inside surface of the wall. The results met our visual expectations, but they were exactly the opposite of normal wall behavior. Normally and ideally, we would expect the moisture to concentrate towards the exterior of the wall. In this case, the less permeable and elastomeric coatings on the exterior of the building had been forcing the moisture to take the path of least resistance, to escape to the interior surface of the 3-foot adobe wall. The salts simply follow the moisture. The moisture and the salts are driven inside the building, where the damage is more difficult and expensive to remediate. This is the opposite of what we would like to see, since interior finishes are typically more costly and harder to maintain. Our expectation was that removing the concrete sidewalk, the cement plaster, and the elastomeric coating and paint would allow the natural wet-dry cycle to resume, with any trapped moisture and salts migrating back to the exterior of the wall. But we wanted to prove it. After removing the concrete, cement stucco, and elastomeric coatings, we sampled the same section of wall again 2 years later in 2015. That chart is shown on the right. It is a dramatically different chart showing a very low and flat gradient. The salt levels at the interior wall surface are likewise now low. There was a significant peak near the exterior wall surface. This gradient is essentially the reverse of the previous gradient from 2 years earlier. This is exactly the outcome we had hoped for. So what has changed between 2013 and 2015? Basal wall stabilization removed loose, friable adobe from the interior of the wall, and with it, significant amounts of salt. The exterior concrete sidewalk was removed, so that we were no longer forcing moisture to the adobe wall. Grading has been slightly improved, though construction was still ongoing, so final grade had not yet been established. The small concrete collar, cement plaster, and elastomeric coatings had been removed. A small band of lime plaster had been applied to both the interior and the exterior of the wall. In other words, we have succeeded in reversing the abnormal flow of moisture and salts in this very salt-affected wall. The natural behavior of this wall has been reestablished. The highest concentration of salts are being promoted to the exterior surface, into the lime plaster layer, which is just exactly what we had hoped to see happen. At the time of this testing, no salt damage was yet visible in the exterior lime plaster layer. For our third and final case study, we'll look at a sample drawn at the Padilla House in Mesilla, New Mexico. This is the gradient of the actual core sample shown being drawn elsewhere in this video series. Here we see a very different gradient that is essentially flat, but with extremely high salt concentrations throughout. While initially puzzling, this gradient makes sense when the history of this particular wall is taken into account. This house, with an adobe foundation, sits on a site that was heavily irrigated with a shallow and very salty well. The wall was repaired and mud plastered several times in 2009 and 2010. Gutters were added to the house to remove ongoing water issues, and grading and drainage was vastly improved. Even though the wall is still actively coving, we strongly suspect that the consistently high levels of salt that we see in the wall represent stranded salts. Though the salt levels are relatively high, by removing the moisture issues, the salts are no longer concentrating along a strong exponential gradient. Though it looks alarming, the wall has actually gotten substantially better after each application of sacrificial mud plaster. So, what can we conclude from these case studies? First, our tools work, and we have demonstrated that we can now measure salts with considerable accuracy. The tools give us a deeper understanding of the microscopic and otherwise invisible processes that are affecting these historic adobe walls. More than repairing physical damage, we think that the ability to detect, measure, and monitor salts gives us a useful new perspective to understand building dynamics. Removing elements that focus moisture, evaporation, and salts is likewise critical. We've conclusively shown that permeable plasters and renders, such as mud and lime plasters, can be used to effectively migrate salts out of load-bearing structure. Migrating salts to the surface of the plaster allows them to be easily removed. Removing salts helps set back the clock for the building, especially if moisture sources are mitigated at the same time. Finally, monitoring and maintenance are absolutely key to effective remediation. Observing efflorescence and any recurring cosmetic issues early and dealing with them proactively can help avoid more serious structural damage in the future. Importantly, these tools only complement traditional preservation best practices and hopefully help to inform effective remediation. Thank you for joining us for this look at remediating salt attack with permeable sacrificial renders and plasters. Please view the other videos in the Salts of the Earth series and subscribe to MVP's YouTube channel.